Hi, this is Professor Stugard, and in this video we're going to discuss the concepts involved with hypothesis testing. So, hypothesis testing. This is when we're doing studies or doing experiments, and I gathered a sample and I want to answer the critical question, how surprised should I be with the results? So, our goals for this video about hypothesis testing. First of all, we want to just understand the main concepts behind hypothesis testing. We also want to learn the procedural outline for hypothesis testing. And of course, both of these things mean a lot of the vocabulary for hypothesis testing. And then we'll see how the hypothesis test might be used in some different contexts. Now, first of all, when it comes to research, it is really important that our results are not going to be due to random chance, but we can never really be sure that they're not, because this world is a chaotic and crazy place and random things happen all the time. But the hypothesis testing allows us to actually determine and assign a probabilistic value, called the p-value, to how likely it is that we would actually arrive at our results. All right? Or what is the probability that our results would arise from random chance? And then we can use that to also determine if our results are statistically significant, which we'll define a little bit more in depth later on. Now, with all scientific testing, it is really, really important that the first step is to define our experiment. That means that although our experiments will differ, we need to set up the hypothesis proportion the same way with a null hypothesis and an alternative hypothesis. Now, the null hypothesis is basically a statement of no change or no effect. And this is basically, it means it's what we should expect. This is what is already out there. This is the baseline. This is what we must assume to be true until we can gather enough evidence to show otherwise. Now, we denote that null hypothesis as H0 or H0, with kind of like that subscript. All right, so the null hypothesis, this is basically the given, what we should expect. And then the alternative hypothesis is the statement that we're trying to prove. So this is the statement that the researcher has come up with. It is the question the researcher wants to study, and he's going to perform this hypothesis test, which means finding the probability of arriving at this alternative if we assume the null to be true. And for our purposes, we're going to use either a normal or a t-distribution to help us calculate those probabilities. And we're going to denote that alternative hypothesis as H1 or H sub 1. Now, the probability that we arrive at our alternative hypothesis is our p-value. So let's just do a few examples and set up the hypothesis testing just to kind of see how it would be done. So let's say GE has just come out with a new LED light bulb that lasts 1,000 hours on average. And so a consumer advocate group wants to know if that average or that mean amount of time is actually less than 1,000. So we set up our null hypothesis. Our null hypothesis is that the mean is 1,000. We need to take GE at their word, and we need to basically assume that what they're telling us is true until we can collect evidence that proves otherwise. And then our alternative, though, what the consumer advocate wants to know, is the actual average less than 1,000. So his alternative, H1, is going to be that mu is less than 1,000. Now, each time we're going to try to sketch a rough normal curve here. And so again, we have to assume the null hypothesis. We need to assume that the peak is at 1,000 because that's what GE told us. And then we want to know what's the probability that it's actually going to be less than 1,000, which means it's to the left, which means that this would be a left tail test. All right. Now, we're just going to set up a few of these. We're not actually looking at them now. I just want to make sure we have this first process down before we can move on. Now, another example. Let's say that we have a 2015 poll that showed that 52% of all Americans supported withdrawing all of our troops from overseas. Now, a researcher believes that percentage is different today. So, step one, set up the null. We need to assume that percentage or that proportion is still the same. So we convert the 52% to a 0.52 proportion. We say, well, P equals 0.52. We need to assume that is true until we collect any evidence to show otherwise. Now, the alternative. Well, in this case, the researcher didn't say whether he thinks it should be less than that number or more than that number. He just thinks it should be different. And that key word right there is different. Every time you see different, what that means is we're actually going to set up our alternative with the does not equal sign. So he just thinks that the probability does not equal 0.52 anymore. Again, we don't know what it is. We don't know if it's going to be higher or lower. We just think it's going to be different. So we think that proportion does not equal 0.52 anymore. What this means is that, again, we have to assume that 0.52 is in the top, but we're actually doing a two-tailed test, which means it could be in either side. And this is going to mean when we actually set up our problems, and we'll do some examples in the next video, we'll see what we have to do with that two-tailed test to account for the fact that we're actually considering double the probability here, right? All right, now the last one. A study claims that the proportion of college students who suffer from anxiety is 0.11, but a statistics student believes that proportion should be higher. So, can you set this one up yourself without me helping? I hope so. Pause the video, write it down, double check, because the null hypothesis is that P equals 0.11, so H naught is P equals 0.11, and the student believes it's higher, which means he believes that P should be greater than 0.11. Again, when we sketch our normal curve, we have to assume that that 0.11 is my mean, it is my peak, and now we're looking for the values higher than it, or to the right, for my right tail test. All right, so if you notice from these examples that null hypothesis is always just either a sample mean or a sample proportion equal to a specific value, typically a previously measured value or claim, although sometimes we don't have claims to base it off of, but that's okay. Typically it'll be given. The alternative hypothesis is an inequality that uses the same value from the null, but uses an inequality. So our alternative hypothesis is always that it's going to be less than, or it's going to be greater than, or it's going to not equal it. We don't know what the value is going to be. We just think it's going to be in some way not equal to what is given to us. All right. Now, in practice, we need to outline our study first, and this includes our null hypothesis, our alternative hypothesis, and level of significance. This must all be done before the researcher collects any data whatsoever. That first step must be done, and nowadays you even need to submit it to a journal first so that you can't go later and what is called hack your data so that you get a statistically significant result when really you shouldn't have. But anyway, you outline your study, including the null, the alternative, and the level of significance before you collect any data. You should also include your data collection methods and how you're going to do that, what your sample size is as well, but that's outside what we're going to do right now. Now, after the hypothesis is well defined, then we collect our data, and then researchers are going to calculate the probability of obtaining the data they've collected that is as extreme or more extreme than what they've actually observed, assuming, of course, that that null hypothesis is true. Now, that probability is our p-value. And at the end of our hypothesis test, the conclusion to this whole study, we either retain the null hypothesis, meaning that we keep it. We said that, oh, well, we did the study and there actually wasn't enough evidence to show what we claimed, so here you go. Here's our study, here's our result. We didn't prove what we set out to prove, but that's okay. We still want to put this data out there. Or sometimes we do get to reject the null hypothesis, meaning that there is significant evidence. We went through the process, we assumed the null was true, we collected our data, and the probability of arriving at our data was really, really small. We had a very small probability. Now, it is also important to notice that we cannot actually prove our hypothesis with this test. What we're doing is simply providing evidence. And that's because, as we should know, there is a lot of random chance out there, which means there's always the probability that we make an error. So, to recap, when we retain the null, we perform that experiment, and the probability of our results, which is that p-value, is large. If we get a big p-value, that means there is a high probability that we would arrive at those results if our null hypothesis is true. So we can't get rid of it. On the other hand, we can reject the null when we perform our experiment and the probability is very, very small. If our probability is small, it would be unusual for us to obtain those results if the null hypothesis was true. This means that our results are statistically significant. And that's actually all that phrase means. When I say statistically significant, that simply means that I was able to reject the null based upon that p-value. Now, we can always make mistakes. Because we're human, everyone makes mistakes sometimes. And at the conclusion of our hypothesis test, when we say we either retain it or reject it, there's always a chance that we made a mistake. And there's two types of errors. There's a type 1 error and this is our typical false positive. We rejected the null when we shouldn't. Basically, the data we collected was extreme, but it was extreme due to random chance, and we probably shouldn't have actually rejected our null, but we did. So it's a false positive. The other type of error would be a false negative. This is when we retained the null, but we shouldn't. This means the data we collected was close to what we assumed with the null, even though most of the data would have been outside. So we have the false positive and the false negative. So real quick, classify the type of error. A fire alarm goes off, but there's no fire. Would that be a false positive or a false negative? Well, false positive, right? It went off, but there's no actual fire, which makes this a type 1. Next example. A Lyme's disease comes back negative, but that person actually has the disease. Is that a false positive or a false negative? That is a false negative, which means it is a type 2. We did not collect evidence to change the null that you were healthy, but we really should have. Number C, a trail guide gives the all clear, but there's a rattlesnake. What kind of error is that? Give you a second. What's your guess? You got a good guess? I hope so. Yeah, that's a type 2. Again, we said that there was nothing there, but there was something there. There was something there. We just missed it. And the last one, the boy who cried wolf, but there was no wolf. This would be a type 1. He said that the wolf existed when it did not. That is a false positive. The alarm went off when it shouldn't have. Now, where does hypothesis testing come into play? Well, besides the social sciences and even the actual hard sciences, this is the entire foundation for our justice system in the United States. Our criminal justice system is set up on this concept of hypothesis testing. Now, this is because all defendants are innocent until proven guilty. And at the start of a trial, a jury is instructed to assume that null hypothesis that the defendant is innocent. Now, I have watched a lot of Law and Order growing up, so yeah, this was pretty straightforward to me. And if you watch Law and Order, they always say this at the beginning of every episode, right? Every defendant is presumed innocent until we gather enough evidence to prove that they're guilty. And so that prosecutor's job is to provide that evidence, just like the researcher. He needs to provide evidence of the alternative, which is that the defendant is guilty or that the defendant is not innocent, right? Now, after examining the evidence, after having a trial, the jury decides to either reject the null and accept that alternative, that the defendant is guilty, or they cannot reject the null. They must retain the null, and they say that the defendant is not guilty. And again, if you've watched a lot of Law and Order or other courtroom procedural shows or movies or whatever, isn't that kind of weird, right? The jury always says, we find the defendant guilty, or we find the defendant not guilty. Why don't they say innocent? Well, that's because with a hypothesis test, the jury can't claim that the defendant is innocent. They can only state that there hasn't been enough evidence to show that they are guilty. All right. Similarly, a hypothesis test can't prove that the null hypothesis is true. It can't actually prove that any hypothesis is true. It just provides that evidence. Now, the jury is always told to make their decision that the evidence shows guilt beyond all reasonable doubt. So what does reasonable doubt mean? Well, it can mean different things in the court system, but let's think about it in the context of the errors that a jury can make. So type 1, that false positive. This means that they think there is evidence when there is not, and they convict someone who is innocent, which is a horrible thing. And the type 2 is they let someone guilty go free, saying that they didn't have enough evidence to say that they were guilty, and that's also a horrible thing. Now, if the jury requires total and complete proof, like let's say they need DNA evidence to convict someone, well then they're going to be more likely to make that type 2 error. And hopefully we can see how they kind of balance out, right? If you need a ton of evidence, well then you're probably going to have a lot of false negatives. If you require weak evidence, well then you'll have type 1s and you'll get these false positives showing up everywhere. Now, again, that's the context of our type 1 and type 2 errors, but I think it's also important to just mention right now that no matter what, there will always be mistakes made. There cannot be a perfect system that only ever convicts the guilty or lets the innocent go free. It's a very sad fact, but it's the way the sausage is made. There will always be guilty people who go free and innocent people who are convicted. That's just the way our chaotic universe works. Now, it is our responsibility as citizens to hold ourselves accountable to the highest possible standards so that we can minimize those mistakes. But remember, there will always be mistakes made. There can be no perfect system. And unfortunately, that does mean there will be guilty people who go free and innocent people who are convicted, and it is sad and it is tragic. And when we find those wrongs, we should right them. But we need to remember that they do happen, and not through any fault of anyone else sometimes, just through the way the system works. All right. Now, back to our actual hypothesis testing and the mathematics. When we are doing the statistical testing, our level of significance is given by alpha. And alpha then becomes our probability of making a type 1 error. So hopefully that kind of makes sense, because that alpha really determines how much evidence we need. Now again, this is a type 1 error, which is where we reject the null when it really was true. And the probability of making a type 1 and a type 2, like I said, they're going to increase and decrease with the level of evidence we need. In an inverse relationship, the probability of making a type 2 error is beta, but we're not really going to talk about that in the context of our Stats 1 class. If you end up taking higher level statistics classes, you might see more about that. But we're going to focus on just that type 1 error. We don't want to make our false positives if we can avoid it. Now wait a second, alpha, we've used that before. We've talked about that with z-scores, and actually it is the same exact alpha. Remember, this is the normal curve. So that alpha from the normal curve is still the alpha from hypothesis testing, because it's all the same exact problem, just looked at from different perspectives. Which means alpha is related to our level of confidence, where 1 minus alpha times 100% is our level of confidence. So again, right, the confidence level and the alpha are basically those balancing points. And so again, alpha represents the area under the normal curve, right, which is why we use alpha like an A for the area under the normal curve, which is also our probability. And that also means that there's a z-score associated for every value of A. So we can figure out how many z-scores we need to go in each direction, right, which is the number of standard deviations. And so you can use the inverse norm function to find that z-score on your calculator. And again, that z-score is known as the critical value. All right. Now, as I mentioned before, this is really, really important for the context of how the world works in terms of scientific studies. That level of significance for a study must be set before the study is actually conducted. Along with the null hypothesis and the alternative hypothesis, we need that level of significance so that researchers can't go back in later and do what's called p-hacking to make their results significant when they really shouldn't be. Now, that level of significance will vary between fields. Typically for the social sciences, we either choose alpha to be 0.05 or 0.01, so with a 5% or a 1% kind of room for random chance, right? Because there's always random chance, but again, alpha equals 0.05 means there's a 5% chance that our result was due to random chance. Now, some of the harder sciences or traditional sciences, that level of significance can be much, much, much smaller. Now, for example, in particle physics, we discovered the Higgs boson a couple years ago, maybe like a decade ago, I don't know. But to do something like that, to state that a new particle exists in the universe, the level of significance they have to use is 5 sigma, which equates to an alpha value of 0.000000003. Or there's a 1 in 3.5 million chance that we made a mistake. And that's called 5 sigma because it is literally we had to go 5 standard deviations away from what is expected to call our result statistically significant. Now, the way this ties into retaining or rejecting our null, if our p-value is less than alpha, if our p-value is smaller than our level of significance, this means that the probability of our results being due to random chance are low, right? P-value is probability, so a low probability means there's a very low chance that it happened randomly, which means I can reject my null hypothesis. We have evidence for that alternative, and this is when we say our results are statistically significant, when that p-value is smaller than alpha. Now, if our p-value is bigger than alpha, well, this means that we had a large probability. This means the probability of our results being due to random chance are high, which means we had to retain the null hypothesis. Right? There's a large chance they happened by random chance or that null hypothesis is true. So, the way hypothesis testing works, step 1, we need to state our null hypothesis and the alternative hypothesis along with our level of significance. Again, this is setting up the entire test before we even collect any data. Then step 2 is to actually collect that data. And of course, we also need to verify that data is going to be independent and approximately normal in the same exact way we did for confidence intervals. Then we take our sample, that becomes our point estimate, and then we calculate the standard error for the null given a sample of that size. So then we can use statistics to find the z or the t-score, depending upon whether it's a mean or a proportion, and then the probability to determine the likelihood of observing that sample using the normal curve or the t-distribution, right? Normal curve for our proportions, t-distribution for our means. So again, step 3 is we find that p-value, and then step 4, we compare that p-value to our significance level we set up before our study even began. And if our p-value is big, we retain the null. If our p-value is small, we reject the null. And then, of course, we need to write up our conclusion. All right, so that wraps up our concepts on hypothesis testing. So can you answer the following questions? Number 1, what is the null hypothesis? Question 2, what are the steps to completing a hypothesis test? AKA what was on the very last thing that I just showed you. And 3, what types of error can occur and how can we describe those errors and what they mean? All right, so hopefully we learned something today about hypothesis testing and how it works. And if you have questions, please comment and ask. Otherwise, as always, take care of yourselves.